1, 2, 3, 1, 2, 3, 1, 2, 3, 1. That should work, I guess.
Okay. So let me introduce you to Mario Lorenz, who received his diploma of engineering. Yeah. Yes, from the Deutsche Telekom Fachhochschule, yeah, in Leipzig. In 2000, he's been working as a research assistant at the Fraunhofer Institute and Technische Universität Ilmenau. Mr. Lawrence's responsibilities include the ongoing research and development on the over-the-air wave field synthesis setup at the Fraunhofer Institute. And his research in integrated mobile communication testing at Vista 4F, and he's working toward his PhD right now. So whenever you're ready.
Yeah. Thank you. Thank you. No. Have to go closer to the microphone, I guess. Okay. Yeah, welcome. As I said, or as I've been so kindly introduced, I am with Technische Universität in Ilmenau, and I'm going to show you some of the things that we have done there together with Fraunhofer IIS. You can kind of regard this talk as a continuation of the talk of Dr. Schirmer. We've been doing most of this work together, so yeah, that's that. The talk that I'm giving here is titled More Economical Over-the-Air Testing, and we shall see why this title was chosen when I go to the details of the testing setup that we have been using, and you will see why it is required to do research in the more economical part of things. Okay, outline of this talk, I quickly go through the motivation, why are we doing this, then I will go on about general testing approaches or general testing requirements, how do you test a mobile UE actually. We will see that these tests can be classified into 3 types of setups, and we will have then some examples for each of these setups, and we will discuss the hardware requirements for such experiments, and then there we will see that it is absolutely required that we have to find more economical means to do these tests if you want to use these tests not only in a university science lab environment, but also in, let's say, commercial settings. I'm doing this for VISTA, which is a German acronym for Virtual Street, which is a setup that we are doing in Technische Universität in Ilmenau, where we actually work together together with a wide swath of research groups and specialties, especially in car engineering. And the idea basically is do virtual drive tests. If you want to do a virtual drive test of a car where you have hardware in the loop, you need to emulate the complete environment that the car is in. So this includes the mechanical environment, so you get to run test setups, test rigs for brakes, powertrain, engine and everything. But since the radio and navigation and communication aspects become way more interesting, we now also have to look into the communication stuff. There's been an industry forum formed about these virtual drive tests. It's the VDT Alliance. and we have a memorandum of understanding with the 5G Automotive Association, which is the body that is concerned about getting 5G developed for automotive purposes. The focus, as I said, is providing these virtual drive tests. So Technische Universität in Ilmenau is where you see here basically the campus. We have several labs with several facilities for braking tests, for automated steering. Actually, this is the drive simulator to do human interaction tests, which are all connected together to provide this virtual environment to get a virtual car up and running. And one part of this whole setup here is the Vista chamber. This is an anechoic chamber, 12 by 12 by 12 meters, where we can put a whole car in and where we can do the electromagnetic stuff that we are discussing here in order to provide the electromagnetic interface for such virtual drive tests. Now the motivation. The fundamental problem of virtual drive testing is that of reproducing in a laboratory either exactly or approximately the system behavior as selected by reality, with my apologies to Mr. Shannon for slightly misquoting him. The idea is you have to have the outside environment, which is basically signified here. What you see, a road somewhere, maybe some mountains or anything else that gives you an interesting channel, which you have to model in some mathematical model, which you then have to reproduce inside your chamber. And you can select the mathematical model any way you want. You can use stochastic models if you want to, but you can also say, okay, I want to actually extract the measurement from measurements of a real drive test that I did, and then extract the direction of the impinging signal components and play that back in my anechoic chamber. So the idea is recreate the channel as you have it outside, inside the chamber, in order to be able to test things. Now, what does testing things mean? Testing things means we are going to test communication systems in the widest sense of things, and that means we put a bit in, we get a bit hopefully back, huh? And what's inside is, in the simplest case, is the black box that we need to shed light into. In this simple model, the system is not even known, the channel is not known or not specified, but still there are already some KPIs that you can evaluate, like what is the bit error rate, what is a delay jitter, and anything that you want in terms of your communication system. The important thing is the test interface, like on which level are you testing the system, and that here is bits. We can now shed light into this black box by saying, okay, this is an electromagnetic radio communication system. So we put there a transmitter and we put there a receiver. What's in between is still unknown, but now we get a couple of new test points at the transmitter and the receiver, and therefore we also get some new performance indicators that we can test. And which are tested in practical, because here you now look into what is the signal power, what is the sensitivity, is the spectrum clean enough that I am emitting, and so on. This is all that you can do when you go down to this level of detail. But nevertheless, it does not even say how transmitter and receiver are connected. For all you know, this can be a cable, but it's not necessarily the case. So when we go to MIMO channel modeling, it's basically the same thing, except that now we have a couple more cables. That's the typical way of looking at MIMO system. And of course, you now get a couple more MIMO-related KPIs in order to test these things, where you can measure correlations and what else. And now we go to the fact that we want to go into a real system where we now even model the antennas. So you have a transmit antenna, you have a receive antenna, and this gives you a new interface to test with, which is the electromagnetic interface. You can model this electromagnetic interface in multiple ways. For now, we can say physical optics approximation. It's a bunch of rays, but we could probably do this any other way as well. And in between, you then still have your radio channel, which you have to model somehow, or have to use a ray tracer or stochastic model or whatever you want. Nevertheless, you can form new KPIs, which is now the absolute directivity of your signals, for example. Now here's a problem. What happens when your antenna or receive antenna system is an adaptive system? Adaptive in the broadest sense, in that it can set weights inside the antenna, as in a hybrid beamformer, or you have a reconfigurable antenna where you turn on or off some of the elements, or even if you have a mechanically moving antenna, you put it into a different direction. This is all an adaptive antenna. If you want to test this, now you have a problem. If you want to use the electrical interface that you used so far, you run into a problem because you will not have the antenna part of the system included in your tests, which is a problem because you need to a certain total system performance. It's getting worse when you look into the complete, fully closed loop MIMO system, where you have the same thing with an interactive system, possibly at the transmitter side, and also you get feedback, channel state information to the transmitter, so that the whole system is more efficient in practical use, but you have to make certain that this really is the case. Huh? So you have now another interaction between formerly separate systems that you need to take into account, because the, let's say, eNode B, to use 4G terms here, needs to select the proper precoding matrix for the MIMO system that we are discussing. So now, objective is we want to do this in a laboratory. In a laboratory, things are slightly different. We have the same, here, we have the same transmitter, and ultimately we have the same receiver that we are concerned about. Inside the laboratory, we typically do not use the original antennas at the transmit side, but we use a set of, here's a nice Stargate style setup. We use a set of antennas that are inside the chamber. They are notoriously different from the ones that you originally have. And to drive these antennas, you typically put in some sort of channel emulation device inside your laboratory, which you electrically connect to the transmitter, which then is connected to the antenna. And inside, or going from the antenna, you now have another transmission channel, and that is the transmission channel that you have inside this laboratory, inside your chamber. So hopefully it's a simple channel if it is an anechoic chamber, but this is not necessarily always the case. And then you go to the receive antenna, to the receiver, and then you get your bits back. The problem of an LTE test in particular is, as already Christopher mentioned, if you assume a small LTE device, then you often have this readily integrated with the antennas, so it's a problem of accessing these test points. So if we compare the system model between the real world, which I've shown first, and the a chamber system, which I've discussed now, using some mathematical license of writing this in a somewhat linear form. I've published a paper about this. It's not entirely accurate because the receiver or receiving ultimately is a nonlinear operation because you have to make the bit decision. But all the way there, it's electromagnetics, and electromagnetics is mostly linear. We basically describe this mathematically the way that, okay, we have our transmitter going to the transmit antennas, some channel, some antennas, and then again to the receiver and so on. So this is the path that you see for the real system here. And this is the same path for the laboratory system, where you have the transmitter going through the channel emulator, going through your emulation antennas, going through the chamber, then hitting the receive antennas, and ultimately going to the receiver. So when we are in such a chamber and want to make such an experiment, we have to look. Let me see what the time is. It's always important. And we have to look, when we want to make such an experiment, and we want to make this experiment cost effective, what are the degrees of freedom that we have? Where can we actually make modifications with a view of either improving performance or cutting costs, whichever way you want. Most want it both ways, but that rarely works. So let's start in this mathematical formulation at HCH, which is the channel inside the chamber. Now, we can influence that, or we can live with preconditions. Most of you would know the anechoic chamber. This is the standard chamber, where you have a metallic cage on the outside. This has the function of preventing any outside interference from interfering with your systems. And what's even more important, it has also the function of protecting the outside from whatever mess you as an engineer create inside this chamber, electromagnetically speaking. However, if it's metal, it reflects, and you typically do not want that. So typically you put absorbers all around the chamber. So your channel or your anechoic chamber makes this HCH rather sparse in the tau domain, because effectively only the line of sight should matter. Everything else should go to the absorbers. You do not need any, in this case, you do not need any resources otherwise to deal with reflections in this chamber. However, if you go on to the idea of just using a chamber, which is not necessarily completely anechoic, and cost savings start with just the idea of not having to cover the floor again with absorbers every time you move a car inside or outside, because that is like half a day's of work. So if you have a chamber that is not necessarily anechoic, you now have a more interesting chamber, which has more reflections there. And the idea is you have to either get rid of them somehow, or you have to use them. If you use, or if you want to do stochastic modeling, a common and standard approach is actually the reverberation chamber. The reverberation chamber is an anechoic, well, partly anechoic chamber, where you have some structure moving inside, which gives you some moving reflections, which under certain conditions can be shown to be stochastically similar to a practical channel on the outside. So that's what is used to test fading channels without much other hardware. It's a very cheap system, however, it is only stochastic. So we've discussed the chamber, then we can go to the emulation antennas in the chamber. And this is also something that you can take influence on. First of all, you can think about how many of those do you need. That's the obvious first question. What kind of pattern should they have? Where are you going to position them for your setup? And the thing is, if you want to make, for example, a wave field synthesis, you have to fulfill the spatial sampling theorem, which is another expression of the sweet spot discussion that Christopher already gave in last talk. So if you have a large device, you need a huge amount of antennas, which, since the amount of antennas is also related to the channel requirement, channel emulator requirements, also means that your channel emulator has huge requirements. You could think of, and that has been done for pre-faded simulation and for other ideas, that you just move the antennas during your tests if you want to change your system. This is something that should be avoided because you have all these cables, which is a general problem. Another idea is you can just move the device under test. Especially on a car, you typically have a turntable which you use when you do electromagnetic or antenna pattern measurements. However, if you look at the system, or if you look at the idea, okay, you drive in one direction, you have one source coming from the left and the other one from the right, and you just drive straight to. They pass in opposite directions, and since you cannot move your turntable in the same direction at the same time, and in different directions at the same time, this is a problem. So the best way to cope with that is to move the electromagnetic field, which in turn means you have to have antennas basically everywhere in a certain density if you want to do that. They have to be distributed equally over azimuth and also possibly over elevation if you need a 3D channel representation for whatever reason. And now we come to the most interesting thing, and that is the channel emulator. The channel emulator is easily the most expensive part of your setup. And that is because you have a set of inputs, you have a set of outputs. You can first discuss the RF parameters that are required. You want to have them in a wideband coverage because you do not know which frequency you're going to measure. You want them with sufficient dynamic range that you can make your measurements, including the channel. You want them to have enough bandwidth for your communication systems, and bandwidth is something nowadays everyone is going wideband and more wideband and even more wideband and split frequency wideband and whatever else, but more wideband. And here's the catch. For wave field synthesis, you have to have them absolutely phase coherent. And that's what making the RF part of the systems like difficult, because phase noise does matter. The next thing, however, is your processing of the emulation or of the channel model that you put in there as a tensor. This is a 4-dimensional tensor. You have an input dimension of a set of inputs. You have an output dimension, the set of outputs. You have a time dimension, because this is a time variant system. This is basically slow time, t. And you have a short time or frequency, if you want to look at it in a frequency domain, for the impulse response of the channel. So if you have if you look at each of these arrows, this is all a convolution that needs to be done in real time of the input signal to the output signal. So you do basically n times m convolutions in this matrix. And this is very expensive if you want to do this in real time for wideband signals. Now, you can look into how to get this easier or cheaper. The obvious thing is to do, since it's a convolution, you put this in the frequency domain, then it becomes a multiplication. This is an optimization that you often have to do, because just otherwise it's completely infeasible. However, the problem with that is now you introduce blockwise processing. And blockwise processing, in our case, means that we have a latency of the system in the order of 20 to 30 microseconds. And 20 to 30 microseconds is about 9 kilometers. So if you now want to test an highly interactive system that was meant for indoor use, you run into a problem. So in such a case, you will have to stick with time domain processing, which then means you have to have fewer taps in the system. So here's basically the main trade-offs that you can do with this channel emulator. And as I said, the one that we have, or as Christoph already said, we have 12 inputs, we have 32 outputs, and this original thing costs in the order of slightly more than 2 million euro. This is research, so it costs money, and that's the point. So, okay. The main thing is you need to make this cheaper. In order to make this cheaper, we have to look again into what is it that we actually want to emulate. And I've found that you can classify this in basically 3 types. Type 1 is you want to emulate the exact electromagnetic field. Either exactly, this is what I call A, or stochastically, this is B. Typically, if you want to do it only stochastically, you can get away with it cheaper, but you cannot reproduce exactly the same field again. Now, type 2 is you want to have the RF port signals the same. Remember, a type 2 system would be the standard conducted setup when you connect to the RF ports of the receiver. But since these are not accessible anymore, we still have to do or to go via the electromagnetic realm, but still just have to make sure that the same signal receives or appears at the receiver. This is basically the wireless cable idea that Christopher also already discussed, and which also has been published in detail. And then we have the type 3 system where you're only interested in identical bit streams under certain conditions. This is mostly used for the standard tests with higher layer functionalities in these car-to-car systems. All that matters is that the systems get their CAM messages for car-to-car driving and so on. So we will see. So again, in type 1, mathematically put, you want to have the output of the real channel identical to the output ultimately after the chamber. So the receive signal that you pick up with the antenna will be identical. This is basically wave field synthesis, or in a slightly different variation, it's also known as power angular spectrum or power angular, what was the other P? Power angular, I forgot. Damn. Yeah, spectrum is the P, and P was profile, I think. I've seen this terminology used in other works. The methods, they basically differ in how you describe the target electromagnetic field and how you get there. If you use wave field synthesis, I refer to the talk that you've just seen by Dr. Schirmer. Now, you can do this with stochastic reproduction. This is basically what I already said. You can have some special cases when the emulator is a diagonal, so you don't have an emulator, but you have a completely stochastic chamber by this reverberation. Then you get the stochastic reverberation, and this has also been done in practice already. Now, if we go to the type 2 setups, where we just want to make sure that after the antenna, both systems match. This is the wireless cable setup, and here this is a setting where we have removed all the absorbers from the chamber. So this is a car inside a chamber, and it's completely reflecting. And we've used the radiated two-stage method. where we use the channel emulator to compensate for all the reflections in the chamber. So you need a powerful channel emulator, powerful in terms of how many taps it can compensate, however, not necessarily powerful in the amount of channels that you need. You can basically, for a 2x2 MIMO system, you can ideally do away with 2 output channels under certain limitations, but nevertheless. You could. And here is a result that we got from measuring there. We measured the isolation between these 2 cables, and you see the problem that you have. They tend to drift over time. So after some time, due to terminal drift, this method kind of deteriorates. When we look into the same thing in stochastics, you can basically say the same, but now you make the channel emulator more stochastic, possibly making it cheaper, but this is a relatively rarely used scenario. Coming back to the possible cost reduction, we have the OTA setup, and here is what we call the mini OTA setup. You see similar devices in the small rack than what you see in a big rack. It's basically the small, or the little brother of that. Oh, wait. Well, yeah, here we are. It's the little brother of this big setup. Cost now only about plus or minus 500 euro, and this is basically the wireless cable setup that we use, and it does have some practical limitation, which we see if I can find the play button somehow. Yeah. This is a car on a test stand, and if I play this again, it's only a short video. You see everything is moving. When you use a car in a practical setup on such a test rig, and you have this dynamometer, the idea is that there are some rolls, and that means that your car is moving. The car means that you are this means that this is going to destroy your HCH, your H chamber, and that means your channel measure, as you have measured before, is not existing anymore. And then that makes, a big problem for you, because the quality of your emulation drops. Just type 3. The bit level is, as I said, mostly not used. We've made a setup with a colleague to determine the antenna pattern just from bit level transmission. So that would fall into this category. And so here's the summary, because I've already seen that my time is over. You can compare these different methods, and you get different effects in terms of price for the hardware. And you see that best is most of the case this type A simulation, but it's really, really expensive. The other things are mostly cheaper, significantly so. However, you have problems, or you get problems with the reproducibility in terms of actual reproducibility, not in terms of stochastic reproducibility. And you get also problems in terms of required RF port access, because sometimes you need, for calibration purposes, access to the received RF ports or cooperation from the device on the test in some way. So that's the summary. I think I quickly go over again. We've seen what we want to do. We've seen how we can do it. We've seen how to cut costs, and the future work is, of course, build better systems, hybrid systems, and cheaper systems to make OTA testing feasible also for smaller businesses. So thank you. Oh, and one thing, if you have got any ideas what else you could do with these toys, we are, of course, also open for cooperations. If you want to do anything there, then just give us a shout in the next break. Thank you.
Thank you, Mario. Any questions? My antenna guys. Jutsu? Nothing? Benjamin? Marco?
Either too bad or too good, I don't know.
Way too good. No, nicely explained. You are working in far-field approximation. Any idea in taking care of a near field?
Yes, there is an idea of getting this closer to the near field. The problem with the far field and near field approximation is where is the difference, right? Everyone says it's near field, it's far field, and you come up with some magical formulas where one is supposed to end. This is not the reality. I have not seen any sign you are leaving now the far field region of this transmitter, right? So that's the thing. If it actually makes any improvement on the synthesis process remains to be seen, because most of these methods are based upon making a calibration step. Also, wave field synthesis is based on making this calibration step first, where you actually measure with this probe the wave field on the inside. So I would not be too surprised if part of the gain that you get from these near-field methods that you could implement there has already been implicitly realized, but as I said, this is an open topic.
Okay, thank you. So, no more question? Okay, so now I would like to call Professor Zurada for the next part of the session. Thank you.